Okay, let's get started. Hi everyone, my name is Kai. I'm a grad student in the UN Zhao group at UC San Diego, and I'll be your host for today's webinar. Before I introduce our featured speaker today, I'd like to remind you to check out our Facebook page called Polariton Chemistry Online Community. That serves as a forum to get notifications about upcoming webinars and updates about recent findings and publications in the field. So please feel free to check that page out. We also have a YouTube channel called Polariton Chemistry Webinars, where we post recordings of each webinar. Here you can go to rewatch your favorite webinar or catch up on a webinar that you were unable to attend. And then finally, as a quick refresher for participation in the webinar, you may use the raise hand option down at the bottom of your screen. I will be alerted that you have a question, and at the earliest convenience, I will notify the speaker at that point at which I will unmute your mic and you can ask your question. We also have a Q&A option in Zoom where you can write your questions. Due to time constraints with the webinar, these questions will be addressed at the end. And with that, I am honored to introduce today's speaker, Professor Chitraleema Chakraborty. Professor Chakraborty received her PhD in materials science from the University of Rochester in 2018. She then joined the Research Laboratory of Electronics at MIT as a postdoctoral research associate in quantum photonics. Following that, she joined the computational materials science at Harvard University as a postdoctoral fellow. She then joined the University of Delaware as assistant professor in materials science engineering in 2021. Her research interests include quantum emitters, 2D materials, integrated photonics, and quantum optics. And with that, Professor, the screen is yours.
Thank you, Kai. I think it says I cannot share my screen.
Can you share now? I just stopped, so maybe. Yeah, there we go.
I hope everyone can see the screen.
Yeah, I can see it, yeah.
Okay. So hello, everyone. I'm Chitro. So I've recently started my own group at UD in January. So today's presentation will mostly be, let me just start the pointer. Okay, yeah. Will mostly be based on the work done during my time at Rochester. And before I begin, of course, I'd like to thank Kai, Joel, and Wei for the invitation and for organizing this wonderful platform. And so today I'll talk about exciton-polaritons in two-dimensional semiconductors like transition metal dichalcogenide monolayers. So 2D materials have been widely studied since graphene, and so far hundreds of 2D materials have been isolated, and they also come with a wide range of electronic properties. So they are layered materials similar to graphene, so you can apply the same techniques like mechanical exfoliation to isolate their monolayers. And the electronic subgroups are also roughly summarized here in this chart. For example, you can have metallic 2D materials or semi-metallic 2D materials, and even insulating material like hexagonal boron nitride. And then you have a range of narrow to wide bandgap semiconductors, and this class of TMDCs like MOS2 or WSE2 are the ones that we will mostly focus on today. So moreover, like while you have those individual monolayers, if you're not satisfied with all of them, you can also mix and match and stack different materials with different properties on top of one another. So you don't really have to think about any kind of lattice matching, like artificial 2D materials that are grown by MBE techniques. As these individual layers, they can be held together by van der Waals forces to give you these completely new heterostructures. And most often they show better performance in a variety of different applications that are listed over here. So, okay. So our lab primarily focuses on transition metal dichalcogenides, so which are called TMDCs. So they have the general chemical formula MX2, where M represents a transition metal like molybdenum or tungsten, and X can be a chalcogen atom like sulfur or selenium. So if you look from the top on the lattice, it basically resembles a honeycomb structure similar to graphene, where the carbon atoms are replaced by alternating metal and chalcogen atoms. And because these two sublattice points are occupied by two electrons, so these materials, they're not atomically thin, but a monolayer of TMDC is 3 atoms thick. So this is evident if you look at the side view here. So you have a layer of transition metal atom, which is represented by these yellow atoms, and they're sandwiched by 2 layers of the green chalcogen atom. And today we'll briefly go over some of their optical properties that appealed to our group and most other groups in the solid state optics research community. Okay, so this is the band structure of exemplary TMDC. So you can see they have layer dependent band gap. So if you look at the bulk over here, the lowest energy transition is an indirect process, which is of course slow and less efficient. And this indirect transition is strongly affected by the presence of neighboring layers. And that is because of the fact that the valence band maxima near the surface are very high. I seem to have a lag, but I hope everyone can see the screen properly and the pointer.
Professor?
Yeah.
Yeah, we can see the screen, but your camera appears to be frozen.
Oh, okay.
But
But the slides are working, right?
we can see the screen and the pointer.
Okay.
There seems to be a little bit of a lag with the audio, a little bit.
Okay. So let's try now, and I'll see like if I can fix this later if this gets worse. Okay. So like I was saying that the indirect transition is affected by the presence of the neighboring layers, and because the valence band
Professor?
the metal.
Professor?
Yeah.
Yeah, your audio cut out again. Could you try maybe stopping your video, like your
Yeah, let me
webcam
try
video?
that.
Maybe there's a bandwidth issue.
I'll just restart this thing. It'll be a minute.
Okay. Mhm. All right.
Okay, can you hear me?
Yeah, we can hear you. Yeah.
Okay. So you're suggesting I switch off the video so this works better, right?
Just as a suggestion, maybe that will fix the issue.
Let's try that.
Okay.
Okay, so the screen share is working?
Yes, I can see the screen. Yes.
Okay, great. Okay. So here, like I was talking about the indirect transition, which is basically in the bulk, you can see the lowest energy is an indirect one. And that originates from the fact that the D and the P orbitals contribute to this valence band maxima over here. So now, if you look at the smallest direct band gap, which is this transition at the K valley, so this is larger in size than the indirect one in energy, and these points originate from the D to D metal orbital transitions at these two points in the valence band maxima and the conduction band minima. So the direct transition remains almost unaffected by the interlayer interactions. So as you go from the bulk to monolayer, this energy remains the same. And that is because the m orbitals, the d orbitals of the metal atom, they are nested inside the sandwich of the chalcogen atoms. But now, as the number of layer decreases, the indirect energy gap increases with quantum confinement, and the lowest energy transition becomes a direct one from the indirect one. So any kind of optical absorption or emission process is enhanced for the case of these monolayers. And for example, you can absorb around 20% of the incident light at the excitonic resonances of these material, and these materials like has also shown a unity quantum yield in some PL processes as well. So we utilize this enhancement and study excitons in these materials. And so here you can see, to characterize the optical properties, we excite an exciton, which is an electron hole pair that is bound together by Coulomb's forces. So when you excite the semiconductor, let's say with a laser with energy greater than or equal to the band gap, you can promote an electron from the conduction, from the valence band to the conduction band, and then you have a hole over here in the valence band. So for the case of monolayers, screening of the Coulomb's forces is reduced because there is no bulk semiconductor, and this results in an exciton binding energy greater than the thermal energy. And for most of the materials, the exciton binding energy is more than hundreds of MeV. So this makes them ideal for studying excitonic physics even at room temperature. So you can see here, this is the PL spectra from different transition metal dichalcogenides, monolayers with different excitonic resonances at room temperature. So along with that, excitons also interact with external fields like external electric field and strain field. So you can use these parameters to modulate their properties like their emission frequency or even their charging state. And in this figure, you basically see electrostatic doping induced population of trions. So depending on if you are hole doping or electron doping the system, you can have a negatively or positively charged trion, as you can also see here in the voltage controlled PL map. So you have a neutral exciton at lower voltages, and then as you increase the doping, you can populate the higher order charged excitonic species. So some of our efforts were based on leveraging the strong optical properties of excitons and integrating them into various optoelectronic and nanophotonic devices. And here are two examples of hybrid plasmonic integrated 2D material based photodetectors. And in parallel to these devices, quantum dot-like emitters have also been discovered in 2D materials, and part of the group is significantly focused in engineering qubits in these 2D monolayers. And in addition to that, we have also used 2D TMDCs encapsulated in these microcavities for studying cavity polaritonics. And this will be the focus of today's talk. So now to start, we are well aware from all of the excellent talks on this topic in this webinar series that embedding an optically active semiconductor in a microcavity results in a variety of different fascinating effects that is related to the resonant coupling of your photons that are trapped inside the cavity with your elementary optical excitations like excitons in semiconductors. And this was demonstrated in 1992 for the first time, where in the strong coupling regime, the interaction between the excitonic state in the semiconductor and the confined light mode in the microcavity led to the formation of these completely two new eigenstates which have different properties than the bare exciton or the photon states. And these collective excitations consisting of part light and part matter quasiparticles are known as exciton-polaritons. And since this pioneering work, there have been a number of different associated excitonic phenomena that have been shown, like Bose-Einstein condensation, or superfluidity, or polariton lasing, spin switching, and so on. And all of them have been discovered in conventional solid state microcavities semiconductor system. So, but owing to the small binding energy of the excitons in traditional inorganic materials, for example, if you consider gallium arsenide, most of these effects can only be observed at cryogenic temperatures. And this makes the cavity polaritonics in these systems quite impractical for real device applications. So part of this issue has been solved by using organic materials and wide bandgap semiconductors, if you think about gallium nitride or zinc oxide. But even for some of these cases, for example, in the organic system, they exhibit strong localization effects because of the disordered potential landscape. And even if you consider the wide bandgap semiconductors, they are basically restricted to the shorter wavelength range, and they also require quite sophisticated lattice matched growth techniques. So now, with that in mind, 2D materials provide a very good platform to realize these polaritonic phenomena, especially at room temperature, because they have a mostly like disorder-free system, and you can grow them quite easily with CVD growth techniques that are relatively inexpensive, and you can also grow them on a wide different variety of substrate. So microcavity polaritons in 2D materials were first demonstrated by Vinod Menon's group. And following this work, if we go back a few years, the focus then had been mostly on neutral exciton complexes, with only a very few efforts with other higher order charged exciton complexes in these microcavity systems. So in the first part of today's talk, I will present a strong light matter interaction of exciton, trion, and cavity photon in a microcavity system. So before I begin, most of this work that will be presented in the first section was done in close collaboration with Dr. Sajal Dhara at Rochester. And so this is the illustration of the device that we have. And you can see the microcavity consists of monolayer molybdenum diselenide. And this is sandwiched between two silicon dioxide layers, which forms your cavity system. And so this is again placed between distributed Bragg reflectors made with alternating SiO2 and Ta2O5 layers. So first we start with the bottom DBr pairs and the bottom cavity, which is grown on a silicon substrate. And following that, we deposit the MOSE2 flake using Scotch tape method and dry transfer method on top of the cavity. And then we continue to evaporate the top cavity and the top DBr layers. So in this way, the monolayer, the semiconductor lies at the cavity antinode. So here we have the reflectance spectrum of the bare cavity. And this basically shows a dip at the cavity resonance around 1.66 eV. And the line width of the resonance is around 3 MeV, giving you a quality factor of roughly 550. And the bottom over here is the PL spectra from a monolayer MOSE2 flake at low temperature. So the spectra shows two dominant resonances. So you can see here, this is the excitonic peak at around 1.66 eV, and this is the trion at around 1.63 eV. And the line widths of these exciton and the trion are almost twice that of the cavity line width. So the natural doping levels in our monolayer MOSE2 are high enough, so it basically supports both the neutral exciton and the charged exciton. So you can basically use these two excitonic species and study the coupling with your cavity resonance. So the cavity is, of course, designed to overlap your the neutral exciton energy over here. So a conventional technique to describe these excitations in the system would involve modeling them in terms of these bosonic oscillator model. So our system over here, the two excitonic particles and the photon, appears quite analogous to this coupled spring and mass system. So this presents a three-coupled oscillator problem involving your cavity photon, your exciton, and the trion species, and G1 and G2 corresponds to your coupling constant. So you would expect to observe three different polaritonic branches: an upper, middle, and the lower polariton branch. So this is somewhat observed by the integrated spectra of our coupled system over here. So you can see this is the PL spectrum of the loaded cavity region with the 2D material. And here you can see three distinct peaks, the upper, the middle, and the lower polariton, which are shifted from the bare exciton and the bare cavity. And this indicates the formation of new eigenstates. So here the spectra you can fit it to three different Lorentzian peaks, which basically tells you that they originate from three different polaritonic branches. So now to confirm the formation of the polariton states, we use this angle resolved PL measurements. So this is the schematic over here. We basically image the back focal plane of the objective onto a camera. And this allows us to collect the PL from the sample within roughly an angular range of plus minus 40 degrees. So each point in the Fourier plane over here corresponds to a particular angle of the PL emission. So this is the angle resolved spectrum from our device, and the color here represents the differentiated intensity of the photoluminescence in the logarithmic scale. And you can see there are three distinct branches. So this is the upper polariton, the middle polariton, and the lower polariton branch. So you can see that the upper polariton and the middle polariton branch, they have a positive dispersion. But now if you look at the lower polariton branch, this has an anomalous inverted dispersion, which is very different from how these two branches of the polaritons look. So this is also highlighted by these spectral line cuts, which were taken from this color plot here. So you can see that the peaks that correspond to the upper polariton and the middle polariton branch, they blue shift from the zero momentum value, but the lower polariton branch, it kind of red shifts owing to this negative dispersion relation. So again, each of these PL was fit to Lorentzian line shapes, and from here we obtained the peak positions corresponding to the individual polariton branches, which we plot over here. So this is the extracted data from the polariton branches. And so here on the dispersion data, we have also superimposed the bare cavity dispersion, which is given in blue, and the bare exciton and the bare trion dispersion without the cavity, which is shown by these dotted lines. So after plotting the peaks in this way, you can see that the effect of the level repulsion between the cavity photon and the exciton is quite clear. And if you look at these higher angle values, the contribution to the branches become more exciton-like for the middle polariton branch, and this becomes more trion-like for the lower polariton branch. So next, we also observed like this Rabi splitting of around 25 MeV at zero in-plane momenta, where you have the cavity photon and the exciton line at resonance. And so again, here you can see that the upper and the middle polariton branch has a positive dispersion, which is quite clear, but the lower polariton branch deviates from this trend and gives a sort of inverted dispersion curve. So now, in order to understand the interaction between the excitons with the cavity photons, we again compare our experiment to this coupled oscillator model. So using this model, we obtain three polariton branches with positive dispersion. So here you can see the upper, the middle, and the lower. And while the upper and the middle polariton branch in our experiment, they kind of match the trend of this coupled oscillator model, but you can see that the lower polariton branch, the lower tran branch, deviates a lot from the model oscillator plot that we have over here. So one important thing that we need to know here, that the trions interaction within the cavity is quite weak with respect to the trions interaction with the dispersed exciton-derived polariton branch. And it is this coupling that kind of drives the physics in our model forward from here. So for our case, the trion dispersion over here was calculated using a mean field approximation, where it was seen that due to the many body effects in the system, the inverted trion-polariton results from an electron-mediated interaction between the exciton-polariton branch and the trion-polariton branch. And this basically, what this does, this overwhelms the weak trion cavity repulsion that you are seeing over here in the model system. And the origin of such an interaction, you can understand it in terms of an exchange between an electron and a neutral exciton and the negatively charged trion. And so this gives the delocalization energy of the trion's electrons, which causes it to look like this, an attractive feature rather than a level repulsion that you would expect normally in the trion-polariton. So next, this inverted dispersion, you can also control it by varying the device temperature. So you can see here, this is the lower polariton branch at 3 different temperatures. And here, this is the zero momentum variation in energy of this point of the trion-polariton branch as a function of temperature. So we have measured this up to 55 Kelvin, and above this temperature, the trion basically thermalizes, and you cannot really resolve it in the spectra. So next, in this temperature range, what happens is you have the bare exciton, which is first red detuned from the cavity, as you can see over here, with a lower value of the splitting. So as you increase the temperature, you see a maximum splitting at around 25 Kelvin, and between the upper and the middle polariton branch over, so this value over here. And then as you increase the temperature further, this energy basically becomes blue detuned from the cavity for higher temperatures, and then you do not end up seeing the trions at all, because again, the trions become unstable beyond this temperature. Okay. So this is the temperature tunability of the effective mass of the lower polariton branch, and this is plotted in the vicinity of the low in plane momentum values. So this can be determined by this equation over here, which is obtained from this dispersion data within this window that is grayed out. So here you can see that this value shows an effective negative mass at the low in plane momentum values. So now this is the same thing, but now a zoomed out version of the effective mass of the trion-polariton branch, calculated from the fit to the data that I showed in the previous slide. And again, like for the trion-polaritons, you can see that the effective mass is negative near the vicinity of the zero in plane momentum for all the temperatures that we have measured. So now if you compare the effective mass of the trion-polariton or your lower polariton branch with the middle polariton branch, you see that the effective mass is positive below the inflection point for the exciton and negative above it. But now if you compare it with the behavior of this lower polariton, it is completely opposite, so thereby producing this anomaly in the dispersion. So this magnitude and the sign of the lower polariton branch effective mass and its extra charge, this basically provides an opportunity to built tunable current carrying polaritonic circuits, and which can exhibit anomalous dissipative behavior. And for future studies, it would be useful to explore how this negative mass influences the effect of disorder and influences the effect of flow on these observed charged microcavity polaritons. So with that, we come to the next part of the talk. And so in the next part, we'll look at some of the...
Professor, we have a question.
Yep.
One second. Go ahead, Hua.
Oh, hi. I found this effect that you're talking about, the concavity of the dispersion, quite interesting. And I was wondering, can you comment a little bit more about the properties of the material that give that concavity, and then what is the maximum concavity that you can obtain? Like, what determines this type of properties? Like, is this a materials property, or is it like something more fundamental?
Yeah, so basically this concavity that we see, so this is dependent. So from the calculations that we had, we could tell that this is basically could be dependent on the doping level, because in earlier experiments where trion-polaritons were studied at the high concentration of trions, this effect was not seen. So basically what they saw was a positive dispersion similar to this your coupled oscillator model. But here, our doping levels are fixed because we are not really engineering the doping. We are not tuning the doping. We have a fixed number of electrons, and then that basically binds with the excitons to form trions. And so we are still in the lower regime of doping, and that is what we think kind of overwhelms this cavity trion interaction and causes this kind of level attraction, because what we think is happening over here is an electron is being delocalized between the trion branch and the exciton branch because of this low density regime that we are working on. And of course, you can tune this further if you use some kind of electrostatic doping device where you can continuously tune in and out the electron in the system, the free electrons in the system. What we expect is this behavior should be reversed, but that is not something that we could do with this particular sample over here, because this is like a fixed device with a fixed concentration of electron.
I see, but I want to understand something. Like, this has nothing to, does this have anything to do with optical nonlinearities, or is really all in the linear regime?
No, I don't think like this has anything to do with the second order optical nonlinearities in the TMDCs. So this is all still in the linear regime. Yeah, but of course, like we only study the exciton-polaritons over here, so I cannot comment on that more.
Okay, but I guess, so sorry, because I am not familiar with the systems, but then, I mean, clearly, if you really fit the three coupled oscillator model with a K-dependent coupling, in principle, you should be able to retrieve this experimentally obtained dispersion, right? So then, I mean, is this really a quantum mechanical effect, or is this something? I mean, ultimately, it's still a linear effect.
So I think I understand a little bit. So this kind of effect is partly due to the fermionic nature of the trion, right? So this model, this is approximated to the boson. This is like a bosonic model, but your trion, like because of these extra electron, it behaves like more like a fermionic model than a bosonic model, unlike the neutral exciton which you have over here. So yeah, like this is like more a material property over here.
Okay. Thank you. Yeah, this is very interesting. Thank you.
And then we have another question from the audience.
Yep.
Go ahead, Binlu.
Hi. So regarding the unusual LP dispersion compared to the oscillator model, I'm thinking is related to the detuning. Like if you make the detuning negatively larger, I mean, what will happen to the lower polariton dispersion?
Yeah, that is a very interesting point. So that is exactly like what I also like hinted at a little bit. So here you can see that the cavity is basically tuned to the resonance of the exciton, which is your middle polariton branch. But then the detuning from the cavity of the trion is a lot higher than that. than the cavity photon over here. So this blue plot. So that's why even with the bosonic oscillator model, you can see that the level repulsion is not as strong as the exciton. So if this cavity were to detune, if you were to detune it with the trion, so this was observed in some of the subsequent experiments done by other groups after this result. So there they have in fact been able to see a positive dispersion. So the detuning also plays a role over here, and that is the reason why this the electron mediated interaction between the trion and the middle polariton overwhelms this cavity and the trion interaction because of the detuning. So yeah, that is also like a very important point.
Okay. Yeah, thank you.
All right, go ahead.
Okay. So let's see. Okay, so like I was saying, like the next part of the talk that will be more about the valley physics in these materials. So we know that TMDCs provide an ideal platform for exploring this valley pseudospin degree of freedom. And in monolayers, you have this metal and the chalcogen atom that form a 2D hexagonal lattice that lacks spatial inversion symmetry. And this breaking of the inversion symmetry and the strong spin-orbit interaction produces valley contrasting physical quantities as well as optical selection rules at the conduction band and the valence band edges, which are located at the K and the minus K energy degenerate points of the Brillouin zone. So further, the conduction and the valence band edges are at the K points. At the K points are formed predominantly by your partially filled d orbitals of the heavy metal, which we discussed a little bit earlier. And this also leads to strong spin orbit splitting of these valence band and the conduction band. So the energy degeneracy of the spin states in the valence band, it is lifted by almost hundreds of MeVs, and you also see the same thing in the conduction band, but with a smaller magnitude. So, and a very important consequence of this spin orbit coupling is that your spin index over here becomes locked to the valley index at the band edge. And consequently, like you can basically selectively excite your spin through the optical selection rule and also like your any kind of intervalley scattering that can happen will be suppressed due to this large momentum space separation between this plus K and minus K valley, as you can see over here. So again, so if you look at the spin valley, spin split valence band at the individual K points, so this also provides protection from the spin and the valley flips. And as a result, you can have a very extremely long lifetime of valley polarization, at least that has been seen theoretically. So this valley contrast can be used to produce, for example, a valley Hall effect, or you can also use optical preparation, control, and you can detect this valley pseudospin polarization using optics. So any information that you want to store here, you can encode it not only by the spin up and spin down states of the electron or the hole, but also by these two momentum indices. So you can, the information can either reside in the plus K valley or in the minus K valley. So in the polarization resolved photoluminescence experiments that were performed on these materials, monolayers. So what was observed that you can basically use a laser to selectively excite electron hole pairs in a valley, which can then form your valley polarized excitons. So thus your the exciton along with the free electron and hole can also have this binary valley pseudospin. So as you can see over here in the PL spectra that was taken by this group in Washington, so they have shown a stronger emission in the copolarized spectra than the cross-polarized spectra in red. So, and this basically creates your valley polarization. So again, like the creation and the detection of the valley coherence is also another important effect of these valley optical selection rules. So if you have a coherent superposition of the left and the right circularly polarized photon, which means a linearly polarized photon, you can transfer the optical coherence of the light into this excitonic valley coherence. So linearly polarized photoluminescence from a neutral exciton has also been observed. So this is particularly for monolayer tungsten diselenide, and the polarization angle of the exciton always coincides with the angle of your linearly polarized excitation laser. So in most of these experiments in the bare monolayers on a substrate, the optical pumping of the valley polarization and the optical generation and manipulation of your valley coherence, all of these have been observed at cryogenic temperatures, mostly liquid helium temperatures. But the major obstacle that you have to coherently control this valley degree of freedom at room temperature is your intervalley dephasing processes, which can be mediated by your phonons, and it can also be mediated by your long-range electron hole interactions. So now with that context in mind, like it has been discovered that TMDC polaritons can also inherit the valley degree of freedom, and this exhibit a very enhanced valley polarization, in fact, at elevated temperatures. And these are some of the earliest demonstrations that we have. So here you can see significant valley polarization was demonstrated from the polariton branches, which are your red and the blue, at higher temperature, but you do not really see any valley polarization for the bare MOS2 material, which was uncoupled. And now the dynamics of these polarization sensitive exciton-polaritons are quite distinct from the isolated valley excitons in the monolayer, and that is again because of your cavity photon component. So this represents your half of the hybrid quasi-particle, which is the photonic part, and this photonic part is basically insensitive to any of these intervalley scattering processes, which are again the contributions from the matter-based depolarization process. So this kind of half-light, half-matter particle results in the preservation of the exciton-polariton valley polarization even at room temperature. And in the next few slides, I will show you how we have leveraged these polariton based on the monolayer TMDCs to circumvent the intervalley dephasing process, and also used it to preserve not only the valley coherence, which were shown in these results, but you can also use it to preserve the valley polarization, but we have shown the preservation of valley coherence as well, along with the valley polarization. So this is our device. So it's pretty much the same as the previous device that I showed, only here we use tungsten diselenide. And the exciton peak over here you can see, which is your black curve, red shifts slightly after the silicon dioxide deposition. And that is likely because of some strain-induced mechanism in the material. And this what this does is this causes a 10 MeV cavity exciton detuning. So this is our cavity resonance in red. And we also confirm strong coupling because we see this anti-crossing exhibited by the photonic and the excitonic branches over here. And again, these two branches, like you can fit them by your usual standard coupled harmonic oscillator model. And for this case, we get a Rabi splitting of around 11 MeV or so. So before I begin this section, Liangyu Qiu was the grad student who worked primarily on this experiments. So this is the schematic of a coherent valley polariton state over here. So what this shows is if you have a linearly polarized laser that excites this device above the band gap of the excitonic resonance. So what it does, this laser populates your excitonic reservoir first, and the coherent superposition of the two valleys in the polariton state can then be created through a fast relaxation process. So this is the photoluminescence spectrum showing copolarization behavior with your linearly polarized laser light at two different angles. And this basically is the first confirmation of your valley coherence mechanism in the polariton system. So here we have also taken the polar plot of the intensity profile at two different input linear polarization. And from this plot over here, you can see that the measured output and the input linear polarizations are they're basically aligned to each other. So this is again another signature of your intervalley phase coherence. And what this also tells you that the excitons are not merely aligned along a given crystal orientation, because as you change the input polarizer angle, your the output linear polarizer also needs to be changed in order to get the alignment of the exciton-polariton right. So let's see. So this is again a exemplary co and cross polarized PL from the polariton device from a coupled and uncoupled flake over here. So as you can see that the degree of valley coherence is higher than the free excitons over here, and this basically demonstrates the superiority of your exciton-polariton as compared to your bare free exciton in a uncoupled monolayer. So so here the room temperature valley coherence in our polaritonic device that we see as compared to this uncoupled exciton is mainly caused by this, like we discussed, the photon exciton hybridization process. So now to understand this valley coherence in a little bit more details and to understand the potential depolarization and decoherence channel, we carry out a polarization resolved photoluminescence excitation or PLE measurement over here. So here you can see basically this is the excitation detuning delta E, which is the energy difference between the laser excitation and the excitonic band gap. So when this delta E becomes larger than twice of the LA phonon energy, the dephasing through the phonon scattering channel is quite efficient over here, as you see, and the valley coherence is significantly reduced. So of course, you also have contribution from the long-range electron-hole interaction here, but the phonon-mediated valley scattering is the most dominant mechanism in our system. So here, what is important over here, that if you look at this region where the delta E values are less than twice of the LA phonon energy, the coherence is partially restored. And as this two phonon scattering channel is kind of turned off. So here, this is our laser excited two phonon occupation number, and the excess laser excitation energy that you have over here above the exciton band gap is basically a source of generating phonons in the system. And these phonons, like I said, they reduce the valley-polariton coherence because of these phonon-mediated intervalley scattering process. So the maximum valley-polariton coherence that we observe will ultimately be limited by just the thermal phonons in the system. And it will also be limited by this delta E energy, which is an additional source of creating these phonons, of populating these extra phonons. So in our data over here, basically we have two parameters, which is the temperature that fixes the intrinsic thermal phonon bath, and that is what determines also your maximum observed valley-polariton coherence. But again, there is scope to increase this degree of coherence if you increase the energy, the resonant excitation closer and closer to this exciton mode, because right now the minimum laser detuning is around 20 MeV, which is still quite far from your exciton resonance. So, okay. So I think, okay, with that, we come to the summary. So what we have seen is that the integrating excitons in 2D TMDC semiconductors with microcavity can basically lead to this anomalous dispersion of your trion-polariton branch, and that is due to an electron-mediated attraction of the polariton branches. And we have also seen the possibility of preserving the room temperature valley coherence for exciton-polaritons, which is otherwise not observed for exciton in uncoupled monolayers. And although the polariton's excitonic component will undergo a lot of depolarization and dephasing process, the photonic counterpart, which these half-light, half-matter particles are made of, they basically offer a fast population decay channel, and this preserves the optical valley coherence. And these kind of room temperature polariton device can provide opportunities for valley-based switching architectures, for example, and they can also provide potential to other valley-polaritonic circuits. So for future work, we'll focus on the time-resolved measurements of these valley-polariton devices, so we can get some more meaningful insight into the polariton depolarization and the dephasing dynamics. And for the outlook, I think it's worth also exploring the possibility of both the charge and the electric field tunable devices in cavity. And for example, in this device, by applying an external electric field bias in two different configurations, you can switch the device from an electric field tunable device to a direct charge tunable device. So the charge tunable regime can help us to quantify the nature of dispersion of trion-polaritons as a function of the density or the population of the trions in the system, and which you can change as a function of this electrostatic doping. And you can also apply this vertical electric field to change the exciton cavity detuning via Stark effect, which will help to understand the effect on the valley degree of freedom of the polaritons as a function of the detuning parameter. So moreover,
Professor, we
yeah,
have a question from the audience.
yeah.
Go ahead. Go ahead.
Sorry, I'll wait for the speaker
Okay.
to finish, and I'll ask. Yeah.
Okay. Yeah. So recently, we have also shown tunability of a number of symmetry-induced property. For example, in these two papers, we have shown modulation of the fine structure splitting in localized exciton, as well as modulation of the valley coherence over here, as well as valley polarization of TMDCs in van der Waals heterostructures at low temperature. And the idea here is to generate a similar van der Waals heterostructure, but now you make this device within a cavity. So in addition to in situ doping, future work should also involve your resonant angle sensitive polariton pumping that will also give you like what is the relation of the valley coherence as a function of these the laser detuning and the angle sensitive pump parameters. So with that, I would like to thank my group members at Rochester, especially Sajal Dhara and Liangyu Q, who were the primary contributors on these results, and all other contributors and funding sources for these experiments. So lastly, if you have any questions, feel free to ask now, or also feel free to drop by an email if you want to learn more about some of these interesting tracks or anything else that you may have found interesting. So with that, I'm happy to answer any questions or discuss anything that you may have.
All right, great. Thank you for the talk. Yeah, so let's start addressing some questions. Go ahead, Joel.
Thank you for the very clear talk. I want to ask you a few questions in regard to the differences between these systems and what we understand about molecular systems inside of cavities. So, for example, like something that we never see with molecules in cavities is PL from the upper polariton. And you seem to, I think you showed a dispersion plot at the first part of your talk where the upper the upper polariton does show photoluminescence. And can you tell me whether this photoluminescence survives at higher temperatures in the upper polariton?
Yeah, sure. For example, for this system that we studied, okay. So this device, this is the data from room temperature, and you can see that the red points are the data, and we still see some signal from the lower values of the in-plane momentum at room temperature. But as we cool down, for example, in this other system, the intensity basically increases. So here, and we also see the the emission from higher momentum values as well.
As you cool down.
Yeah.
Okay. Wait, but then if you now so in terms of the valley coherence, um, okay, so I guess you pump the reservoir states. So then with, you know, with thermally activated processes, in principle, you should be able to observe PL also from the upper polariton. Do you see that?
Yeah, we do see that. We do see PL from the upper polariton.
Is it also polarization conserving?
Yeah, so it is not as the degree of the polarization is not as high as the middle polariton.
Wait, which is the
So basically, like you can see the reason, I mean, the reason we were not able to observe this because our laser detuning was within this range. And so this was where we were scanning the laser over here, right? So we are only able to see a fraction of the upper polariton, just this part. And there was also like for the near resonant conditions, we could not observe this quite clearly because there was a lot of leakage from the laser itself. But so we ended up looking at these higher detuning values where this signal was signal to noise was clear, and there the polarization was not as high as you can see in this near resonant values. So this was like a technical challenge for us because if your laser is parked over here and the signal is right over here, then our collection of the system was not efficient enough that would filter out the near resonant laser. So we could only study the non-resonant conditions, and at the non-resonant conditions, similar to the middle polariton, the upper polariton did not really show any degree of linear polarization.
Okay, so I guess the last question I would ask you is, in these phonon-mediated processes from the reservoir into the polariton, um, do you, I'm sure, I mean, based on what you have described, there are several of these processes that involve the polarization of the excitation, but then is there also a sizable fraction of these phonon-mediated processes that conserve polarization?
So let's see. So we can explain this.
I guess every PL
Yeah.
event involves a phonon mediated event. Would you agree with that statement?
So basically, like if you just look at the dynamics, so in the cavity you have these dephasing process and the valley depolarization process, and this is the lifetime of the cavity and the excitonic radiative recombination. So basically, like what you basically depend on this to the numerator and the denominator, the fraction of this term determines like how much degree of linear polarization will be preserved. And now if you look at if you go back to what you were talking about, let's see, where is my slide on the, okay, here. So yeah, so this is, so we have this model over here, and here you can see this model consists of two valley resolved excitonic levels. So these are the K and the K prime valley. And so this is the helicity resolved cavity modes over here, right? So the coupling of the cavity photon and the exciton results in these coherent transitions between the K and the K prime valley. And these are marked by this interaction terms, and the four states that are connected to the ground state are by this individual population decay. And so what we include is both this population transition or the intervalley scattering, which is your pure dephasing process between the two valleys that accounts for the valley polariton depolarization. And you also have these valley polariton decoherence and depolarization process from these two from dephasing of the two cavity modes. And this is neglected because we know the TETM mode splitting of the cavity mode is quite small. So the major dephasing process is then your phonon mediated intervalley scattering term. So although we have these other depolarization mechanisms, the major contributing factor is this two phonon mediated scattering process. especially because for these dielectric cavities, the TE-TM mode splitting it's quite small. So that does not create, that is not the major contribution of the depolarization over here.
Okay, but very quickly, but in this model, you are not including the, the relaxation process between the reservoir into the polariton state. So then I want to understand that step a little bit more, like, because normally I would imagine that that step really kills a lot of the polarization, and then you showed, and many people.
No. Yeah, exactly. Like I said, we do consider the polaritons as well. And so basically, if you're just considering the normal excitons, the dephasing, then depolarization in normal excitons, you see it as your long range electron hole interaction, and you do see the phonon scattering. But even now, considering the cavity, what is the source of depolarization of the cavity? So that source is your normal mode splitting, the TE-TM mode splitting.
Yeah, but
Right?
sorry, that is not what I'm asking.
No.
I'm asking about the reservoir into the polaritons, right? So then that involves a that involves a phonon decay, right? Like, because the excitation energy is not the same as the emission energy, as you have emphasized, right? So in that phonon decay, uh, I guess what I want to understand is, why is there not a very strong depolarization in that process? And I believe that in the model that you're just showing right now, that is not accounted for, or unless I am not understanding.
I'm not sure if you're asking about the thermal phonons in the system, or if you're asking about this two phonon scattering, which is controlled by our the laser detuning.
Can you explain very quickly again these two phonon scattering, and then maybe I'll ask offline the rest. Yeah.
Yeah. So basically, so what we see over here, so the scattering, so the phonon scattering mechanism. So this is the K valley and the K prime valley, and the two phonon mechanism. This basically causes a the scattering process basically causes a depolarization between the K and the K prime valley. And this energy is being supplied. So the energy is being supplied by our, again going back to our laser detuning energy. So right over here. So this energy over here from the exciton, and this laser detuning again depends on your population of your two phonon occupation number, and this is basically what we are showing over here in the PLE measurements.
Okay, I guess I don't fully understand the two phonons, but I will look at your paper and then ask you later. Thank you. Sorry about that.
Yeah, sure.
And then we have a question from Jeff Arutsky. Oh, Jeff.
Okay, I couldn't figure out how to unmute. Can I just ask, is there evidence for, I guess I would just say, what's the temperature dependence of the broadening and the contributions to the broadening outside the cavity at these temperatures?
So, yeah. So, I don't think let's see. So, of course, like just intuitively, like if you are reducing the temperature, so what you are doing here is the thermal phonon bath that we were talking about, the scattering because of the thermal phonons, that gets reduced. And like initially I said, there are two different limits on this device. So one is the thermal phonon bath that kind of controls how much your degree of coherence will be. And the other is this laser detuning. So that controls your this two phonon scattering processes. So here in this experiment, our temperature is fixed, but we are changing this detuning process, which is changing the degree of linear polarization. But now if you change the temperature and you keep decreasing the temperature, this value is expected to again increase a little bit.
Okay, thanks.
And if there are no more questions, then Professor, if you will allow me to share my screen. Great. Okay. Once again, Professor, thank you for that interesting talk. And I just want to remind you all that next week, our guest speaker will be Maxim Sukharov from Arizona State University. And I will see you all next week. Thank you.